Hello, this is our house price prediction model for our machine learning project. Before we go over the introduction, here's just a little picture showing how much housing prices have increased over just a small time period. So the objective of this project is to develop a model for predicting home values using the 1990 California census data sets. And we want this just so we can have a reliable way to predict housing prices for home buyers, sellers, and investors. Our data set uses a diverse data set using various property features, geography, and historical pricing. Our approach is to apply many of the machine learning methods that we have learned in class for accurate property value estimation. And this is to meet the rising demand for trustworthy property valuation models, as well as to improve decision making with high accuracy property value forecasts. So home buying is a pretty significant financial step in the U.S. And with how uncertain the market is, it can be very challenging for first-time homeowners to pinpoint the best time to buy. So the benefit of our model is it would allow homeowners to gauge the optimal time to purchase a house and around what price they could expect based on just whatever factors such as size of the house or just where it's located. So overall, the model would aim to bring certainty to a very volatile housing market.
We're going to use the California Consensus Housing data set. So we're going to do residential property values in each district in California, and then variables for house and residential information. And it's 1990, but it is okay to be 1990 because we can adjust the inflation easily. So for data pre-processing, we're gonna do data cleaning, remove the null entries and redundant data during the initial phase, and then data transformation, like apply log transformation to skew variables like total rooms and like total bathrooms to get shape closer to normal distribution, and feature an analyst to explore the relationship between like the ocean proximity and housing prices. So this is like before applying log normal and then after applying log normal histogram. And then this is the longitude and latitude, so proximity to the ocean can like raise the property value kind of thing. And then this is like the heat map, shows us the correlation of like the ocean proximity features.
So we mainly used 4 models in addressing this problem. We used linear regression, ridge regression, random forest, and gradient boosting. And we used the root mean squared error and coefficient of determination as comparison metrics between the different models. So the linear regression model, this provides valuable insights in visualizing the geographic influence of ocean proximity on housing prices. And after we trained our linear model, the next step was to analyze its accuracy using the root mean squared error and the coefficient of determination score. So we had a root mean squared error of $65,150.27 and a coefficient of determination of 0.6793. So that root mean squared error is not normalized. So the way you can understand this is that our model is off by around $65,000 for each property value. And as expected, it's not the most accurate at predicting the real data points, but we use these later on to compare the different models that we have to see which one is the best. And then, as you saw earlier with the heat map, some of the features were highly correlated, and this is where ridge regression comes in. It's great at addressing multicollinearity issues in our linear regression model. And introducing this model led to a marginal improvement. The root mean squared error reduced slightly, and the coefficient of determination score marginally increased. So really the impact of multicollinearity was not a huge issue, as you see from the metrics for this model. Since if there was a significant impact of multicollinearity, we would have had greater performance gains. So now we pivoted to using a random forest model instead. So this is an ensemble learning technique. And so the way this works is it uses the technique of bootstrap aggregating or bagging to pick a random attribute at every split. Ideally, this would drastically reduce the variance of the final classifier. The use of a random forest model would also reduce the risk of overfitting and improve accuracy at the cost of slower training. Our random forest model had significantly improved performance over the original linear regression and the ridge regression model, with the root mean squared error of $49,176.32, with a regression score of 0.8171, and this was without any tuning of the hyperparameters. So when we looked at, then we just looked at tuning some hyperparameters via cross-validation. So we looked at max depth, min sample split, and number of estimators. And the root mean squared error decreased to $48,867.95, with the regression score slightly increased to 0.8193. Now we pivoted to gradient boosting. So this is an ensemble learning method which combines several weak learners into strong learners. And the illustration on the bottom right kind of shows that iterative approach of doing that. And so the predictions from these models are combined into one model. And then theoretically, this is usually outperforms random forest. So, and it is also, it is more resistant to overfitting. So with the default hyperparameters without any tuning, it actually had a higher root mean squared error compared to random forest and a lower R squared value. However, after tuning hyperparameters with cross-validation, like the max depth, min sample split, and number of estimators parameters, the root mean squared error reduced drastically to $47,000 roughly. And the R squared made a huge jump to 0.834.
In our analysis of predictive models for median house values, we found significant differences in performance. The linear regression model showed the lowest accuracy, and even with ridge regression optimization, the improvement was minimal, suggesting limited impact. When comparing random forest and gradient boosting under default settings, random forest initially outperformed. However, after fine-tuning, gradient boosting slightly edged out in performance. Our benchmark for acceptability was a coefficient of regression score above 0.8. Both random forest and gradient boosting met this criteria. And if we decide to continue with this project, these are some of the next steps we can take.